Hi, we're going to talk about the material in Lecture 22 today. Lecture 22 is the second lecture on hypothesis testing. In the first lecture, we talked about the idea of hypothesis testing, about the form statistical hypotheses have to take, and so on. Right? You remember that whenever you actually try to do a hypothesis test, you have to start out by writing down the null and alternative hypotheses. That's H naught for the null hypothesis and H sub A for the alternative. Right? The null hypothesis for us, we only talk about hypotheses about the mean of a single population, so we have null hypotheses of the form mu is less than or equal to some number mu naught, mu is equal to some number mu naught, or mu is greater than or equal to mu naught. Right? Those are the only three possible null hypotheses for us. The corresponding alternative hypotheses are the negations of these. So if your null hypothesis is mu is less than or equal to mu naught, then your alternative has to be mu is greater than mu naught. And similarly here, the negation is mu is not equal to mu naught, and here less than. Okay. It's worth emphasizing again that the parts with the equals parts, the less than or equal to, greater than or equal to, those only occur in null hypotheses, and the greater than, not equal to, less than, only occur in alternative hypotheses. The reason I keep saying this is because when you read a problem, sometimes the claim will be the population mean is greater than or equal to some number, or not more than some number, and then it's probably related to the null hypothesis. But the claim may also be that the population mean is less than some number or something, and then you would know that that should only be an alternative hypothesis. Okay, once you have the hypotheses, then you can think about testing them. So for example, let's take a hypothesis, a null hypothesis of the form mu is equal to mu naught. Right? How do you test such a thing? Well, of course you remember, you take a look at sample means. Right? Here's the sample means curve, the x-bar curve. If this null hypothesis is correct, then the center of that curve, the mean of it, is the number mu naught. And if that's true, then if you took samples all of the same size, I don't know, whatever size you were talking about here, right, you have to be large enough, most of those sample means would be right near mu naught. Again, if the null hypothesis is correct. Most of the sample means will be right near mu naught, with only a few far away. And so evidence against the null hypothesis would be to find a sample mean that was pretty far away, like over here, right? Or maybe over here. Doesn't matter which side in this case, just that it's far enough away from mu naught. And we could compute, as we did last time, right? If we knew the population standard deviation here, we could compute the probability of seeing a sample mean at least as far away from mu naught as the one we actually saw. Let's say we saw this one. Well, the probability of seeing any sample mean for a sample of this size, whatever size this is, at least as far away from mu naught as the one we actually did see, would be this little area plus this little area. So in this case, it's okay. We'll think it's a bad idea if the sample mean is far away in either direction. The sum of those two little areas there, that's called p, the p-value, it's often called. And if that p-value, the probability of seeing a sample mean at least as far away from mu naught as the one we have, if that p-value is too small, we're going to reject the null hypothesis. We're going to say it's probably not true. Okay? Well, what we'll actually do, we won't set cutoffs on the axis. What we'll actually do is we'll set a cutoff probability before any of this begins, before we start doing the test, right? Or even collect a sample. We'll set a cutoff probability called alpha, and this is the name of this is the significance level. And then if this probability here, the probability of seeing a sample mean as bad as the one we saw, that is as far away from mu naught as the one we saw, if that probability is less than or equal to alpha, the significance level, we will reject the null hypothesis. That's our test. That's basically a hypothesis test. Now again, we'll do the calculations on the calculator to actually see these numbers, but that's the idea. If you had a null hypothesis of the form, let's say, mu is greater than or equal to some number mu naught, you get the same kind of picture. Let's suppose this is mu naught. So the claim here by the null hypothesis is that mu is to the right of that. It's over here somewhere, mu. If mu is something to the right of mu naught, right, then the sample means, the curve for the sample means, the x-bar curve, will look like this. Right? It'll be centered on that number mu. And evidence against this null hypothesis would be a sample mean far enough to the left here. One that's, right, the null hypothesis says the population mean is over to the right of mu naught, over here somewhere. If we find a sample mean that's all the way out here, then that's evidence that this null hypothesis is incorrect. And the interesting probability here is the area underneath the x-bar curve, that is to the left of this number. I'm going to call it x-bar naught, just to give it a name. If the probability, this area to the left of x naught is the probability of seeing a sample mean that is as bad as the one we actually saw or worse. That is as far to the left of mu naught as the one we actually saw or worse. Well, what's the maximum that probability could be? The maximum that probability could be, so the best chance we can give this null hypothesis as being true, is if we actually assume that mu is equal to mu naught, right? That would make the sample means curve look like this, and now the area to the left of x bar naught is larger. It's as large as it can possibly be. This is as far to the left as we can think of mu being while still making this true. And that gives this null hypothesis the largest probability possible of being true. Right? So that's what we're going to do. We're going to use the same kind of picture we used up here to test this. Right? So we're going to assume, given this kind of null hypothesis, we're going to assume this kind of curve where you have mu naught in the middle. But we're going to accept as evidence against the null hypothesis any x bar that's too far out to the left here. And we can compute the probability of finding an x bar that's to the left of, that's equal to or less than the one we actually found. And if that probability is again called p. And the same rule is used. If that probability, p, is too small, that is, if it's less than or equal to the cutoff probability alpha, then we will reject this kind of null hypothesis. This kind of test up here, this kind of test is called a two-tailed test. That's a two-tailed test because we're interested in the probability under both tails, the area under both tails of the sample means curve. This one is called a left-tailed test, and I don't suppose I have to tell you why. Right? And similarly, if you had a null hypothesis of the form mu is less than or equal to mu naught, then evidence against that would be an x bar too far to the right, and you'd get a right-tailed test. Okay, here's the problem. A company claims that the amount of cereal in its 24-ounce boxes is normally distributed with mean 24 ounces and standard deviation 1 ounce. You have checked 30 boxes and found a mean of 24.5 ounces. Test the company's claim at the 0.05 significance level. So first thing we have to do is ask a couple of questions. First question is, can we apply the CLT. If we can't apply the CLT, we can't do any test at all. So we have to check that first. When can you apply the CLT? When you have an approximately normal population. And here we are actually told that we do. It says a company claims that the amount of cereal in cereal boxes is normally distributed. Right? So they're claiming that for the whole population. So yes, we have that. The other situation in which you can apply the CLT is if you have sample sizes of at least 30, and here we have that as well. So yes, we're good. We can apply the CLT. Second question we have to ask is, do we know the population standard deviation sigma? Right? We're going to see two kinds of tests. This kind, the kind we've talked about already, is called a z-test, and that's the kind you can do if you know the population standard deviation. So you read the problem carefully and see if it gives you the population standard deviation. The company claims that the amount of cereal, etc., is normally distributed with mean 24 ounces and standard deviation 1. They are telling us that the mean is 24 and the standard deviation is 1 for the whole population. So yes, right? We know that sigma is 1. So we can do a z-test. Okay, now we need 5 numbers to do a z-test. We need mu naught, the number involved in the claim about the population mean. We're going to need sigma. We're going to need n. We're going to need x bar, the sample mean, and we're going to need alpha, the cutoff probability or significance level. Okay. Mu naught, the number involved in the claim about the population mean. Well, it's pretty obvious here. A company claims that, etc., that with mean 24 ounces and standard deviation 1 ounce. So the claim is that the mean is 24. So the number involved in that claim is certainly 24. Also, we're told the standard deviation, and that's 1. The sample size is 30. We have checked 30 boxes, so the sample size is 30. X bar is the mean of our sample. The mean is 24.5, so let's write that in, 24.5. Alpha is the significance level. Fortunately, it's usually given as a decimal in problems, so it's 0.05. So now we have all 5 of these numbers. The next thing we want to do is to write down our hypotheses. What are our null and alternative hypotheses? Well, I'm going to just read this problem because I don't think we have to go through any process here. The company is claiming that the amount of cereal in its 24-ounce boxes is normally distributed with mean 24 ounces, etc. There's no claim that the population mean is greater than some number or less than some number or no more than or no less than or anything like that. They are claiming it is 24 ounces. That's going to be our null hypothesis, mu equals 24. And of course, that means our alternative hypothesis is mu is not equal to 24. Okay, we have everything we need to do the hypothesis test, which of course we do on the calculator. So here we go. Let's turn this on. You do a hypothesis test on the TI calculator by going to Stat, press the Stat button. I hope you can see that. Let's move the slide away a bit. Press the Stat button, and then arrow over to Tests. Z-test is the very first one, so you just want to press Enter. Now right in the beginning here you have a choice between data and stats. This is a problem with stats. A problem with data would actually have data which you would have entered into list L1. This one has stats, and it makes a great deal of difference. Right? If you go over to data and hit enter, you'll see that the menu changes. You can actually have different choices. So you need to put this on the highlighting on stats and press enter. And now you can go through and put in all of the numbers from the problem. Mu naught, right? That's the number involved in the claim about the population mean. It's 24. Sigma, the population standard deviation, is 1. X bar is 24.5, the sample mean. Right? N is 30. Right? Just type it in. And now down here, you get to choose the alternative hypothesis. You can choose mu is not equal to mu naught, mu is less than mu naught, or mu is greater than mu naught. In this case, of course, it's mu is not equal to mu naught, the alternative hypothesis. And then you go down to calculate and press enter. And it'll give you a bunch of stuff, most of which you don't care about. What you do care about is this p value right here. Right? P in this case is about 0.006. So we have p is approximately 0.006. Now the question is that enough to reject the null hypothesis? It is, because alpha, remember, is 0.05. So we have p less than or equal to alpha. That is, we have 0.006 for p and 0.05 for alpha, and that's certainly less. Right? And since p is less than or equal to alpha, we can reject the null hypothesis. In words, it's a good exercise to say it in words, and it's also required many times. In words, you would say something like, this data, or this sample, whatever, does not support the claim that the amount, let's say, average amount of cereal is 24 ounces. Okay, the big shortcoming of z-tests, the kind of test we've been doing so far, is that they require you to know the population standard deviation, sigma. In real work, you almost never know the population standard deviation, and so something else has to be done. And the thing you need is what's called a t-test, and that's the same kind of thing as a z-test, based on the same principle, but you use the sample standard deviation to approximate or estimate the population standard deviation. Right? You end up, as I said, with something called a t-test. And there's a bunch of stuff in the book about t-tests and how they're kind of like z-tests and so on, but I'm not going to go over any of that here. I'm just going to talk about when you should use each one, and then I'm going to do an example of a t-test problem. So, when do you use z, and when do you use t? When do you use a z-test? When do you use a t-test? And the rule is very simple. First of all, you must be able to use the central limit theorem, right? So have n greater than or equal to 30 or an approximately normal population. You must be able to use the CLT to do any kind of test at all. And I promise you there will be problems, both from me and on the final, where I do not write all the problems. There will be problems in which you are asked to do a hypothesis test and you won't be able to apply the CLT. Right? And you just have to be aware, because the right answer is going to be don't do the test. Okay, just be on your toes. Okay, assuming that you can apply the CLT, the answer here, when to use Z and when to use T, is if you know the population standard deviation sigma, then you must use a Z-test. Otherwise, you must use a t-test. It's as simple as that. Make sure you can apply the CLT, or else answer, I can't do this test. Once you know that, then you can decide whether to use Z or T. If the problem tells you the population standard deviation, then you must use Z, otherwise you use T. Okay, here's a problem. The XYZ Corporation has told its staff that the average salary of a secretary is normally distributed with a mean of $22,000. Janet believes that the average is really less than that and has found 10 secretaries in her area and their salaries, which are listed below. Write her null and alternative hypotheses and test her claim at the 0.05 significance level. All right, so let's do the questions here. First, can we apply the CLT? Well, that's a pretty small set of data there, but it turns out we are told that the average salary of a secretary, that's the population here, is normally distributed. So yes. So we can go ahead and do a test. Second question is, do we do a z-test or a t-test? In this case, we definitely do not have the population standard deviation. In fact, the problem doesn't give us any standard deviation. But in particular, so here's the question, do we know the population standard deviation? No. So we're going to use a t-test. All right. In order to do any kind of test, you're going to need to be able to write down the null and alternative hypotheses. So let's go through those steps here. Right? So we need the hypotheses. What's H naught and what's HA, the ho and the ha. Let's go through the steps for finding the alternative hypothesis. First of all, what's mu naught? Whoops, what's mu naught? Well, mu naught is the number involved in the claim about the population mean. Here, where the claim is that the average salary of a secretary in this corporation is normally distributed with a mean of $22,000. So mu naught is, come on, I can write that, 22,000. That's mu naught. Right. Okay, now that we know that, if we are given a sample mean, x bar, then we can do something. But here we're not given any sample mean, right? We're just given data. The truth is that we could get the sample mean by putting that data into a calculator and looking for the sample mean, but we're told explicitly in those rules in the previous section not to do that. What we're told to do is, when we're given data, to go with the wishes of the researcher. Janet here believes that the average salary is really less than 22,000. So that's going to be her alternative hypothesis. Mu is less than 22,000. And then the null hypothesis has to be the negation of that. Mu is greater than or equal to 22,000. Okay, we have enough information to do the test. Oh, actually, we need one more thing. At the very end, we're going to need to compare our p-value with alpha. And alpha is explicitly given as it must be. Alpha is 0.05. Notice that the significance level, the alpha, never goes into the calculator. It's got nothing to do with that. After you compute the p-value, you compare it to alpha, but you never put alpha into the calculator. All right, so let's do this. So we're going to go to stat again, and then over to tests. But this time we're going to go down to the second entry, which is t-test, and press enter. And we get a choice. Oh dear, we have data this time, so we need to put the data in list L1. So we'll go to stat, and then edit, and there's list L1. And you can see I've already put the data in. All right. So now stat, over to tests, and down to t-test. All right. We have, again, to make a choice between data and stats. And you'll see the menu changes quite a lot if you choose the other thing. So here we have data. We need to choose data. We need to put in mu naught, right? The number involved in the claim about the population mean. There it is, 22,000. List is L1, right? And that's where your data should be. Freak, you don't touch that. It's always going to be 1 in this class. And now the question is, what's the alternative hypothesis? Well, we know its mu is less than 22,000, less than mu naught. So put the highlighting on that and press enter. Then go down to calculate. And again, there's a bunch of stuff here that you don't actually care about. And then there's a p-value about 0.0547, call it 0.055. So p is approximately 0.055. Now we need to make a decision. Do we reject the null hypothesis? Do we have p less than or equal to alpha? That's when you can reject, right? If p is less than or equal to alpha. But here we do not have that. No, right? Because p is 0.055 and alpha is 0.05. So we can't reject H naught, right, the null hypothesis. To put this into words, we could say these data do not support Janet's claim that the average salary is less than $22,000. Okay, that's pretty much it for lecture 22.